Okay, so this is like it's connected somehow. Yeah. Okay. But is that just for the YouTube recording? I guess so.
I frankly don't know how they do it, how it goes. Thank you for coming over. We'll start in the next session. Just a couple small things. Please keep your mobiles in silent mode so that we do not disturb the speaker. If you are going to exit or enter this or any other rooms, please be quiet with the doors, they're quite noisy. Small announcement today at 4:30. We will have a competition with prizes. This will be in room D105, so everyone is welcome to come over and compete for the prizes. That is all about the organizational announcements, and please now welcome Jesper, who will be talking about the stuff that he'll be talking about.
Yeah, thank you.
Welcome, please.
So yeah, I'm going to be talking about some of the challenges we have with the network stack when like the equipment starts to get quicker and quicker at increasing speed. So I've sort of taken a challenge to make the kernel stack scale to 100 gigabits. So what will you get out of this? Also try to actually, there will be a lot of numbers, and I'm sure I'll lose half of you like in the middle of the section, but I actually want to try to give you something also, to give you an understanding of what's going on with this, what is so crazy about this time budget we have when doing this extremely fast network. And I'll also talk about some of the accepted changes we've done recently, accepted changes in the upstream kernels. And I also actually I moved this up. So the memory allocation limitations, I was going to talk about that in the future section, but now it's actually mostly done. So, and then in the future section, I'll talk about what we still need to do. So we are definitely not done yet, even though I think I've been working on this project for like 2 years or something. So 100 gigabits is coming really soon. So what happens when the network speed increase? What happens is that the time between the packets gets smaller. So then that means the network stack and the software has less and less time to process each packet before a new one arrives, to sort of keep up with the network. So if you look at the time scale, look at big Ethernet frames. So there's like, with 10 gigabits, there's like 1200 nanoseconds between the packets, and they correspond to like 800,000 packets per second. And then 40 gig, we still have like around 300 nanoseconds between the packets, and it corresponds to like, you have to handle 3.2 million packets per second. And then we go to 100 gigabits. And now we're starting to get into trouble because there's only like 123 nanoseconds between the packets, and that again corresponds to around, we have to be able to handle 8 million packets per second. So that sort of challenges the network stack, and what can we sort of do about it. So I've actually recently got some 100 gig NICs, but most of my testing is actually done on 10 gigabit NICs, and what I do to sort of simulate the worst case and pressure the stack to the edge, so I can like improve the performance, is that what I did is I turned down the frame size to the smallest Ethernet frame size you can send, and then I calculate what's how many nanoseconds. It's like 67.2 nanoseconds between the packets. That's the worst case situation I can create. So I'm using that to see when I improve the kernel. In that case, it will also improve it in like the longer use cases. And I'll be ready for when the 100 gig NICs arrive. I'll talk a lot about this number here, but what you should actually look at is how many like CPU cycles is this, because it's difficult to relate to this number. But so with 3 gigahertz, we have like 200 CPU cycles for each packet. We can of course like buy a faster CPU, but it's only 269 packets, 69 cycles. So, and another thing is that they actually do exist. The 100 gig NICs do exist. I have 3 of them. I actually took a picture of you, so you actually believe me. So, actually, it says 100 gig. So I have in my lab, I've been testing with them for some while now. Not too long, but it's fun to play with new hardware, right? So, is it at all possible to do with this kind of hardware? So at least with 10 gigabit, there's some kernel bystack solutions out there, and they have been growing over the recent years, and they've sort of pressured us into like looking at the kernel and looking at ourselves and saying, do we really use the hardware optimally when like out of 3 bypass solutions can do something faster? And because it is a very artificial benchmark, like stuff like GPDK does, but they actually show that with the same hardware I have, they can forward the smallest frame size, and they do it on a single CPU. It's a little bit fake benchmark. You just take in the received descriptor of several of them, and don't even look at the packet, and just put it over in the transmit ring of the hardware and say go. So it's fairly fake, but they do show the hardware can actually handle these speeds. So why can't the kernel? So this is a little bit controversial because I'm upsetting the other kernel developers. So everybody has been working on like just scaling the kernel to multiple CPUs, and it's been really great. The kernel, like, quite impressive work to make the system scale and make it like scale perfectly for several cores. That's really nice. But what we've been hiding a lot of regressions for the efficiency per core. That's what I'm saying. And I actually also claim that doing this we have affected the latency sensitive workloads. So I think we should look at improving the efficiency per core. So for example, for IP forwarding, we are doing like 1 to 2 million packets per second for forwarding IPv4 packets. The kernel does scale up. It scales up if you have like to 12 million packets per second, if you have enough CPUs. But I have a little hard time with just the bypass solution says, okay, they can do it with one CPU. I want to do better. But also it is like comparing, a little bit like comparing rockets with airplanes. Like rockets actually just have to fly up and shoot really faster. But airplanes, we have to carry passengers, and we have to actually pack the passengers in the plane, and we have to make them comfortable. You don't have to be comfortable in the rocket, and we have to take package out again, and they have to get their luggage. So we're more airplane type of a solution. So now I'm going to try to explain you this crazy time scale. It'll be interesting to hear afterwards if anybody actually understood it. See if it blows your mind. So this time scale is crazy. I already mentioned that we only have like 200 cycles. But for you to understand this time scale, I'm going to relate it to some other time measurements, so you can sort of get a picture of what are we dealing with here. So I did a lot of the benchmarks. All these benchmarks are mostly on this type of CPU. It's actually not that fast with the gigahertz, so we can get a little bit faster if we just crank up the gigahertz. But let's see what is on this specific CPU, what happens. So I measured like a single cache miss is 32 nanoseconds. Oh my god, that's not good. What was my budget? It was like 67 nanoseconds. Uh-oh, just 2 cache misses. I'm out of my budget. That's not good. And then looking at, we have something called a SKB, which is a metadata structure for the packet. It's 4 cache lines. Oh no. And we insist on writing zeros every time we allocate a new one of these. Uh-oh, have I done lost already? Well, not exactly, because it's not full cache misses. They're usually very hot, so they will either be in level 3 or level 2 cache. So I went ahead and measured that. So, like for the L2 cache access or miss, it's like 4 nanoseconds, and maybe if you're really unlucky, 8 nanoseconds. Well, that's like a time scale I can use. I still have a chance to actually do this. Another thing is we will sort of always have a cache mesh on the packet data itself. But then Intel is coming and helping me a bit because they have this new smart feature they called Data Direct I/O, where they will actually deliver the packet data in level 3 cache. So I only have a hit of 8 nanoseconds for accessing that. So okay, it's looking good. But then we have these time synchronization mechanisms we have to do in the kernel. So every time you take a lock, that's an expensive operation, so I measured that. So yeah, there's something called an assembly instruction, a lock prefix. So I measured this on this specific CPU, it's like 8 nanoseconds, so that's not so good. So that's just for locking. I also have to unlock it, so I also measured that. And actually also, so it takes 16 nanoseconds. So it's starting to eat up of some of my budget. I shouldn't have too many of these, right? And there's funny issues going on if you have, like, if there's actually 2 CPUs. This is like the optimal case. If there's actually 2 CPUs contesting on the same line, you're out here. But we figured that out in kernel. We're doing like really good scalability. I also written down, I measured on 3 different CPUs and measured the cycles because the nanoseconds cost is a little bit strange because the nanoseconds is a time measurement, and time measurement depends on the gigahertz you are running, and you can just crank up the gigahertz and do that faster. But if you look at the cycles is much more stable between CPUs, so you can actually measure this number a little bit more. So, what happens if you actually need to talk to user space with your system call? First when I measured it was like 75 nanoseconds. I thought this was like never going to fly. So, and then I actually found out that the profile, and I found out that the audit sys call was causing quite a lot. So we're down to around 42 nanoseconds. It is a large chunk of my budget. So should I worry a lot? Well, I should rewrite my user space applications to use some of the APIs we actually already have. Like I see almost no applications, this is only for UDP, these two, but I tried to search the internet, and almost nobody uses the extra M in the send message and receive message, which allows you to have multiple receive and send messages. So I wrote an example how to use it and put it on my GitHub and hope someone else will pick it up. But we also have send file that's been really popular. It gives a huge performance difference for serving files on the web server, for example. And we have other tricks where you can actually avoid the system overheads of doing one system call per packet. So we should be fine. I just think that a lot of applications might have to actually start using this. So another thing you have to do when you're optimizing this, you have to know the time scale for different synchronization mechanisms. So I started benchmarking that. And this is on another CPU, so that's why the log doesn't correspond to what I said before. But this corresponds to mostly in cycles. So I discovered something which was quite weird for me. So this is the cost of locking and unlocking, so 34 cycles. And then we have something where we just disable the local CPUs, or the local IAQs on the CPU. And it was more expensive than taking a lock and releasing it. What's going on? So that's with the save and restore option. So you have to save the CPU flags. That's apparently quite expensive. If you avoid, like if you already know what interrupts state you're in, if you already know the interrupts are on in this context, you can safely just disable it and enable it again. The problem is if you don't know the context, you have to save it before and restore it. So you make sure you're not having them layered and you're not. So you can actually save quite a lot. You can save like 30 cycles. That's quite amazing. If you can replace one of the save restore with just a disable enable. So we did that some places in the kernel where that made sense. So how do these, like we've seen all these numbers and when they add up, it's like, how can we do this? This sounds like an impossible task. What's going on here? So how did the other guys manage this? So the main trait to illustrate, that's batching. Batching is like doing all different kind of levels to see what's going on. And another thing is we found out was the transmit queue. I think I have some more slides about that. So we have all kind of tricks to do pre-allocation and pre-fetching, and of of course, staying on the same CPU. We're already quite good at that in the kernel. There's some of the things that give us our scalability. And of course, avoid the logging, we saw the cost before. And there's also shrinking the media data, reducing the syscalls, we've talked about that. So faster cache optimization of the data structure, aligning them correctly. We've done a lot of that work in the kernel already, and something we like to do. I also want to lower the instruction cache misses. It's something which we haven't optimized a lot. It's something that the compiler does solve for us. We try to do a little bit in the kernel. We know some hot functions. We are inlining them to make the instruction cache prefetcher more efficient. But we haven't really optimized it a lot in the kernel because it's actually sort of invisible. We're really good at using the perf tool to measure stuff, but instruction cache misses are very difficult for the performance part. I want to actually see. But let's look at the main fundamental tool, which is sort of batching. So the main challenge we have here is that we have a per packet processing cost, and that's sort of what's the issue here. So we only have this very small amount of time for each packet. But if we just use batching or bulking, then we actually have some opportunities. So, but sort of word of caution that we should only do it where it makes sense. Like the bypass solution just always bulk, because you can actually introduce latency if you just always bulk and wait for opportunities to bulk. So I want to live in that area where we actually try to avoid introducing latency. That is sort of, I think, the value that the kernel can bring, that we do a solution where we will scale all the way up without fakely introducing latency like the bypass solutions does now. So a really simplified explanation how we can sort of increase our time budget. So we just remove the per packet overhead, and for example, if you just say, okay, I'm always processing 10 packets in a bundle or a batch, then I can basically just multiply the time I have. So now I have like 672 nanoseconds between each of these 10 bundles coming in. Then I have to handle the next 10 bundles. And it's oversimplified because it's not that easy. But so basically, that means I have 2,000 cycles. Man, I can do that. And that's basically what like DPDK, they always take 32 packets. They sort of wait for them, and then then you sort of have a lot of time budget if you can amortize away all the overheads per packet. This is a little bit more difficult in practice. So what have we actually done recently? Quite happy that this section of my slides are getting bigger and bigger. But we actually did sort of the biggest achievement last year was we figured out how to sort of what I call unlock the true potential of the hardware of the transmit side. So basically the lowest level of the driver. We have this testing tool called package-gen. We can now demonstrate that we can actually with one CPU on Linux transmit to wire speed 10 gig, which is like 14.8 million packets per second. So we're down to only using what's it called, 67 nanoseconds per packet. So it is cheating. We're just spinning the same packet and stuff like that. So, but the primary trick, what is going on, is that we are bulking packet descriptors to the hardware. So I had a really hard time figuring this one out because I had optimized the packet-gen. We went from to start with, we could only send 4 million packets per second, and we were like reusing the same SKB also. So, but we could only go 4 million. Then I optimized it like everything I could to 7 million packets per second, and then I couldn't move any further, no matter what I did. And then something looked strange. There was a log costing a lot, but this log was not contented. So this look strange. That's the only thing I could see in my perf profiles. There's this lock of the qdisc layer was consented. That's strange. I'm running a single CPU test, and it's supposed to scale perfectly, and I'm sure that nobody else needs this lock. We calculated, took my calculations, and well, it's supposed to cost like 8 nanoseconds, but it costs way more. It was like several hundred nanoseconds. Something must be wrong. So then I started trying to, okay, I'll just remove the lock. I'll just compile a kernel without this lock. Because, of course, if some other traffic came, the kernel would crash. But this is my test lab. I can do that. And then all of a sudden, there's like this one assembler instruction was blamed for 80% of the time. That doesn't make sense. So I tried to change something else, and then the instruction just moved. What? I can't figure this one out. So what it ended up, I finally figured out that it's because we are writing the tail pointer down to the transmit in the hardware, and this is a sort of a PCI write. We cannot see, the CPU cannot see it. And the CPU tries to be smart, and then next time it sort of gets back, or the next atomic operation will be blamed. Some Intel guys later told me that's what's happening, that the next atomic operation will basically get the blame because you cannot show what the CPU is doing at this point in time. That was quite interesting. When I then did the changes of figuring out that you could delay, if you just delay the tail point right into transmit, put several packet descriptors down, and then write the tail. Then I jumped from 7 million to like 13 million. And I was like, this cannot be true. Something wrong. Had to double check all my results. Yeah, it was true. And then we took from the 13 million, and then we optimized it like to the full wire speed. It was quite exciting to see the jump in from 7 to 13. So, I always have this. I don't want to introduce latency. I could just wait for packets and just do this blocking. It would look really good. But I want to try to see how can we integrate this in the kernel without introducing more latency. So we actually have implemented it. So what we did is we have now what we call an xmit-more API. So we extended. So the way you use this API is that we extended the SKP with an xmit-more indicator, which is just a bit. So the stack uses this bit to indicate to the driver that another packet will be arriving like immediately after this. Also, I promise the stacks give the driver. I'll make sure that I have one more packet for you when I'm just going to return. That's a sort of a promise that the stack gives, and the driver says, okay, I'm going to get this packet. So unless my transmit queue is filled, if it's filled, I will flush it. It can simply add the packet to the hardware transmit ring and defer the expensive indication to the hardware. So that's nice. Now we have this feature. But when should we actually activate this? Because the hard part is using this without introducing latency. That's one of my goals. So we should only talk when it's really needed, and we should base it on some solid indication from the network stack. We could just speculate, like delay a little bit on the transmit. It's really hard to resist because the benchmark looks so good, right? But it's like DPDK, so I'm not going to fake these. I want the correct technical solution for the kernel. So what we ended up doing is we changed like the transmit layer, and we adjusted it so you can send SKP lists down the transmit layer. And when you send a SKP list down, you will see that the SKP next pointer is set, and we'll simply just use that as an indication if there's more packets when we are in the transmit loop. So this also helps. There's a what we call TXQ lock, which is the lock down to the driver. Before calling the driver, the network stack takes a lock. So another CPU cannot call the same driver on the same transmit queue. And then we assign sending this entire SKB list and releasing the lock. So that also helps us amortize that lock down to the driver, and then we amortize the tail right. And then we have this. We already have actually packet activation going on in the network stack today. It's something called generic receive offload or generic segmentation offloading, and we also have some hardware feature called TSO, TCP segment offloading, where the hardware delivers sort of a bigger packet. So we already have this feature, at least for TCP, it works quite well. And the lower receive layer, we will see if we can build up a packet, a super packet consisting of several smaller SKBs and sending that down. So that was sort of easy to allow those to be bulk transmitted down towards the qdisc layer, which was really nice. And I'm not introducing any added latency. This beforehand had actually introduced a little latency for TCP, but it's not really a problem. Then there's some. We also did some. We could do some validation in a step where we didn't have a lock, but that's another optimization. So this was the existing one. So what did we do for the qdisc layer? So looked at the qdisc layer and then realized, okay, if there is a queue in the qdisc layer, in the queue, then it's the most solid indication that you can start blocking. So that's what we implemented. So packets have already been delayed, so it's sort of easy to construct this list and avoid this adding latency, because the latency have already happened. It's when you look at it, it's actually one of those really rare cases where we have been bunched some packets together, but now we have it in the queue, and instead of doing per cost per packet now, we'll realize this and actually lower the latency for experience with these packets by taking out a big chunk of them and sending them on. And we also have a lock down to the qdisc transmit. It's only the DQ side we have implemented now. We don't have an NQ side. I'll be working on that. But so the DQ side, we have amortized the cost, because we'll just take the lock once and we can pull out several packets. There's some extra locking costs. I'll come into that later. So another thing we chose to do. So one problem when we start to do this bulking down towards the hardware is we can overshoot what the hardware actually is capable of handling, and then we'll send a return code saying, I cannot handle this. And then what should we do with these packets? Should we drop them? No. We have a qdisc layer. Can we re-queue it into the qdisc layer? No, because we have this complex structure of qdiscs. We support that. So qdisc layer right now does have hang it off and do a head of line, sort of head of line blocking, but this is the next packet we have to transmit, because the hardware just sort of stop all in the middle of this flow. So we chose that we will only do this for drivers who has implemented something called BQL, byte queue limit, which is a way of avoiding buffer bloat, if you know that term, implemented down in the drivers to avoid too much outstanding packets in the hardware. And the experiments are really good. I'm not going to implement requeuing into the individual qdiscs and support for that, because the results were so good. So we also have done a lot of other optimizations. One of the most prominent is the optimization of the flip lookup, which is the route lookup. And Alex Dyke, he improved that a lot. It's like crazy. Together with a lot of other optimization, we basically made the IP forwarding performance. We doubled the IP forwarding performance on the kernel. So that's been really cool. So I only have 10 minutes left. But this is like a good summary slide of what we've achieved over the past 2 years. So for the lowest layer, I started at 4 million packets per second, as I talked about, and we can actually send like full wire speed now with Linux. So, and the lowest receive layer, we still have some work to do. This is all a single core test. So we started at, this is still fairly experimental results, but we started at 6 million packets per second. Now I'm optimized it to 12 million packets per second. This is only the lowest layer, so that's why I can do so quick optimization. Just pushing the lower layer and ignoring what goes on. If I do IP forwarding, we optimize it for doing 1 million packets per second to 2 million packets per second per core. So if we do multi-core, we have quite good scalability. So we actually, for multi-core, I think this was an 8-core machine. We actually do 12 million packets per second today forwarding the smaller packet size. And that's a real 7.2 benchmark. So what do we need to work on? Well, I have a talk next week where we only talk about what we should work on. And I don't get the introduction of how we actually understand the nanoseconds. So we have a lot of, actually we are still not taking full advantage of our transmit powers or our transmit capabilities I've been talking about. I still see stalls on this tail point on the right, indirectly by looking at the log from the qdisc layer. We also have some limitations in the receive layer we have to deal with, and sort of the baseline overhead of the qdisc, we have to lower that. And memory allocator is hitting the slow part. I'm also optimizing the memory allocator. We have some cache misses we have to fix. Let's see if you have time to look at all the slides before I'm pulled out. Now we've got the overview. So transmit looks really good. So how does receive perform? So remember we have to reach 8 million packets per second with big frames to dealing with 100 gig driver. So I tried the 100 gig driver, but disappointed to see like the 6 million packets per second. I talked to you about I'll do the driver tests where I'm dropping that, so I optimize that to 12 million. I use a lot of tricks there. I avoid a cache miss. I do a more efficient instruction cache use. I use most of the overhead there is memory allocation. So I optimize the memory allocator to do bulk allocant free, again to amortize, do bulking, sort of a general term, a general theme going on. And you are actually also, for this case, had to tune the swap allocator. I'll try to put into the kernel so we do more automatic tuning of this for different use cases. So I sort of extrapolated what I believe I can pull out, so I believe I can optimize to like 19 million packets per second in that lower layer. Okay, so I also want to only 5 minutes. So I also want to optimize instruction cache misses. So one thing I noticed is that if you combine with GCC5 instead of GCC4, it's much better at inlining the right stuff and laying out the code correctly. And I saw like a ×10 reduction in the instruction cache misses and the performance going up like significantly, like I don't know, 100 nanoseconds or something, more 200 nanoseconds maybe. So there's a lot of gains to do in this. So I want to optimize and do some stages where we process these bulks of packets. I think I'm going to rush instead. So I identified that the memory allocator was a bottleneck of in the network stack. The optimization is almost done, but I'll just explain to you what's going on. So we did this artificial receive benchmarking, dropping the packets early, then we don't see the memory allocation problem. But the real use of the network stack, what's going on, it has too many outstanding packets. So in the receive layer, we actually pull out 64 packets, put it into the transmit ring, and then the problem arises because we have to wait. We do DMA transfers, and we have to wait to the hardware to say transmit completion, and then we can clean up the packets which are in the DMA engine says it's done with. And then we end up, we have at least 256 outstanding SKBs. And this causes the slope allocator to hit the slow path of the allocator. So I identified this and used quite some time to optimize the allocator. First I implemented a layer on top of the memory allocator and just to do a show me the code example of I can do it faster than the memory allocator. Then people objected to that they're doing a cache on top of a cache. So I had to like go in and fix the real memory allocator. So it's actually quite impressive result. So the normal slop fast path is like 42 cycles, but we are actually hitting the slow path, which costs 100 cycles. So, like, actually I have, yes, I have optimized this also. But yeah, so what happens is that I'll just do bulking instead, and I can reduce it quite a lot. So actually look, if you bulk like really a lot of elements down here, I'm at 37 cycles, and that's faster than I can do with the fast path. I'm really happy about that work, that we actually get a huge performance benefit with that. The patches are on the mailing list and will hopefully soon go in. And then we have something about base overhead of the qdisc here. I'm not going to go into that because I don't have time. But I estimated we use like 70% of the time is used in docking operation. So we should do a lockless qdisc. So we just need to do that. And John Fasterbrand from Intel has actually proposed a solution for doing the lockless qdisc based on a lockless queue I implemented. So a little bit commercial. All of these changes most of these changes have been backported to Red Hat 7.2, and we saw enormous performance boosts there. So Alex did us. You can look up Alex's talk from LinuxCon, where we actually showed we actually doubled the route performance after Red Hat kernels with all this work. So that was quite impressive. And then I have like a talk next week with all the other kernel developers about what we should do about all the things I talked in the future section. So anyone have questions?
You were talking about latency, not about jig. How these all optimizations actually change the jig for them? Or it's not necessary, it's done gigabit per second.
Yeah, it will, like the jitter, and I'm very worried about the spikes we're going to see when we start to do buckling. But in reality, I'm trying to find out measurements, the way I can do the measurements. Because the way I'm doing measurements now is I'm taking this large time scale, which is 1 second. It's very large, and we can have many spikes within this.
Perhaps your specification doesn't see much changes in any way.
Yeah. But I look at it this way: if like you have maybe I delay the first packet a little bit, but I think I'm getting a lot better latency if you do it this way. If you have the elevator and it's only you go into the elevator. You don't. If there happens to be more people, all of the people go into the elevator, and they actually see less latency instead of each individual person going all the way up the elevator or through the network stack, what we have doing today, and returning, picking up a new packet and returning. So by putting up these, I'm actually removing a lot of latency since I executive packets. So I'm hoping not to introduce too many latency spikes.
How do you test 100G to have information to 90 or do you use like a generator?
I use
which I basically don't know.
Because you mentioned that you are using blind cards for practical solution. Are you happy with the numbers?
Yeah, I'm quite happy with it. There's a lot of things that they need to optimize. And I'm going to help them out with that. So no problem. But some of it is not their fault. It's the network stack that needs to adapt to this new challenge of such fast network counts. So I'm going to cooperate with them, and they send me the links for free, and I have my loan, and I'm just happy to play with new hardware. And you want, you should get one.
Okay, guys, we are
I think I'm out of time.
So
Thank you.
please take the
I'm going to upload it on my.
Can you copy it for
Yeah.
the organizers? Yeah, just.
Oh, that's for the organizer. I thought you were just one of them.
I think I'll be going over there now. So this airplane versus rocket analogy.
Yeah.
Is it kind of like atomic host versus atomic enterprise?